Have you ever stopped to wonder just how much data we process every single day? In the current era, data has evolved beyond the scale of millions to reach the staggering billions. Take the LAION dataset as an example. It's a nonprofit organization providing massive datasets for AI training. It features over 5.85 billion image-text pairs. Or take CERN, the European Organization for Nuclear Research, which houses the world's largest particle accelerator. Every second, particle collisions generate up to 1 petabyte of data. Even after filtering, they are left with over 5 billion events to analyze, just to find a rare physical particle or an anomaly within that vast sea of data. When data becomes this massive, humans can no longer look at it directly to understand its content or internal structure. We need mathematical tools capable of automatically identifying structures at an extreme scale. So, we are drowning in a petabyte ocean of data. What is our lifeline? The answer lies in two fundamental solutions. Today, we will dive deep into the first core pillar, clustering, while keeping dimensionality reduction in our toolkit for later. But before we throw complex math and code at the screen, we need to understand what clustering actually means from a scientific and psychological perspective. According to Gestalt principles, our brains are hardwired to recognize structures and patterns subconsciously. We do not calculate distances in our heads. We just see it. For instance, look at this. When dots are closer to each other, your brain instantly groups them together. This is the principle of proximity. What if they are equally spaced, but have different visual traits? Boom! Your brain immediately separates the pink dots from the white ones. That is similarity. We also group things by boundaries. Draw a box around a set of points, and they instantly become a family. This is the common region principle. For us humans, these principles, symmetry, connectivity, common fate, are incredibly intuitive. We understand them at a glance. But here is the ultimate challenge for data scientists. How do we encode this deeply human intuition into a mathematical algorithm that a cold, logical computer can understand? That is exactly what we are going to build next. We saw how human brains use complex Gestalt principles to group things. But computers? They don't have feelings or intuition. In computer vision and machine learning, we have to brutally simplify all those subjective factors into one single, cold mathematical concept: proximity. To a machine, similarity is just distance. The more similar two objects are, the shorter the calculated distance between them must be. But how do we put complex things, like images of pigeons or hummingbirds, into a math space? Enter representation learning. We feed raw, messy data through deep neural networks. The network compresses this data and projects it into what we call the latent space. If the algorithm performs well, all critical features are preserved, and similar items naturally gravitate toward each other, effectively pre-clustering the data. Here is the catch. In supervised learning, the AI has a cheat sheet. It is provided with labels. It learns the representation and assigns the clusters simultaneously. But big data is messy. It rarely comes with labels. Welcome to unsupervised learning. In unsupervised scenarios, the data might be grouped together perfectly in the latent space, but the computer is completely blind. It doesn't know what the clusters represent, nor does it know how many clusters there actually are. They are just anonymous points floating in the void. Therefore, the true essence of a clustering algorithm is to solve this final mystery. It is the automatic discovery of these hidden boundaries, and the assignment of every single data point to its rightful family. Let's dive into partition-based clustering. The absolute titan of this category is the k-means algorithm. Imagine you run a clothing brand and need to decide on the perfect sizes for small, medium, and large shirts. K-means is your best friend here. But first, you must manually tell it how many clusters you want. This is the K in k-means. The algorithm starts by blindly dropping k random centroids into our data space. Then begins the endless loop of optimization. Step 1. The assignment phase. Every single data point scans the area, measures the Euclidean distance, and pledges allegiance to the closest centroid. Step 2. The update phase. The centroids look at their new followers, calculate the mathematical average of their coordinates, and physically move to that new center of mass. This cycle repeats until no points change sides. But how does k-means know if it did a good job? It uses a metric called within cluster sum of squares, or inertia. It measures how tightly packed the points are around their masters. Lower is always better. This brings us to a massive dilemma. If lower inertia is better, why not just make k equal to the number of data points? Because then every point is its own cluster, which is completely useless. To find the optimal k, data scientists use the elbow method. We plot the inertia for k equals 1, 2, 3, and so on. The graph drops sharply at first, but at a certain point, adding more clusters doesn't improve the score much. The curve bends like an elbow. That exact bending point is your optimal number of clusters. Despite its elegance, k-means has a devastating weakness. It is hopelessly biased towards perfect circles. If your data doesn't look like perfectly round grapes, k-means will fail miserably. Look at this stretched out, elliptical distribution. A human sees one single group, but k-means, desperate to draw circles, will brutally slice this natural shape in half. To solve this rigid geometry problem, we ascend to a more sophisticated model, Gaussian mixture models, or GMM. Instead of calculating simple geometric distances to a center point, GMM uses the covariance matrix. This matrix allows the algorithm to understand not just the center, but the variance, the width and the angle of the data. Just like k-means has a sign and update, GMM uses a powerful statistical loop called the expectation maximization algorithm. In the E step, it performs soft clustering. It doesn't force points into rigid boxes. Instead, it calculates the probability that a point belongs to a specific Gaussian distribution. Then, in the M step, it adjusts the mean and covariance to maximize the likelihood of the data. This flexibility is what makes GMM the absolute standard for dealing with complex, overlapping datasets. We have seen the power of k-means and GMM, but both share a frustrating limitation. You have to guess the number of clusters in advance. What if the data could reveal its own structure? Enter hierarchical clustering. This approach doesn't just group data. It builds a family tree, known as a dendrogram. The most popular method is agglomerative, which builds this tree from the bottom up. Initially, every single data point is considered its own isolated island. The algorithm searches the entire space for the two closest islands and merges them into a new, larger cluster. It repeats this process. Measure, merge, until all points are united under a single giant root. To get your final clusters, you don't need to guess k in advance. You simply slice the tree horizontally at your desired height. But there is a trap. How do you measure the distance between two distinct clusters? This is called the linkage criteria. If you use word linkage, the algorithm tries to minimize variance. Sadly, it falls into the exact same trap as k-means, ignoring true geometry and forcing everything into spherical blobs. To capture complex, irregular shapes, data scientists switch to single linkage. It defines the distance as the shortest gap between any two border points. It beautifully hugs natural curves. But single linkage introduces a deadly new vulnerability: the chaining effect. Imagine two completely distinct crowds. Now, drop just one or two random noise points in the middle. Because single linkage only looks at the absolute closest neighbors, it sees these noise points as stepping stones. It builds a bridge across the gap, and catastrophically swallows both distinct crowds into one massive, incorrect cluster. Pure distance measurement has failed us. To conquer complex shapes and completely ignore noise, we must abandon distance and embrace a new weapon: density. We have seen how distance-based algorithms get easily fooled by strange shapes and bridge building. Noise. To survive in the real world of messy data, we must abandon pure distance and embrace density. DBSCAN relies on two simple, yet powerful parameters: epsilon and min points. Imagine epsilon as the radius of your flashlight in the dark, and min points as the minimum number of neighbors you need to form a crowd. If you turn on your flashlight and see at least min points number of people within your epsilon radius, congratulations, you are a core point. Here is where the magic happens. A core point doesn't just form a cluster. It starts a chain reaction. It reaches out to its neighbors. If those neighbors are also core points, the cluster expands, swallowing connected points like a viral contagion spreading through a network. It perfectly maps out irregular shapes. And those lonely points completely in the dark? They are labeled as noise and are safely ignored. DBSCAN is a masterpiece. But what can go wrong? The fatal flaw of DBSCAN is that it uses a single global epsilon value. This creates a nightmare if your data has uneven densities. If you set epsilon too small, the dense clusters are found perfectly, but the sparse cluster is completely dismissed as useless noise. If you increase epsilon to capture the sparse points, the flashlight becomes too wide. The distinct dense clusters bleed into each other, merging into one giant, useless blob. You cannot win. To conquer the uneven density problem, we must evolve. Enter HDBSCAN, hierarchical DBSCAN. HDBSCAN abandons the single epsilon radius. Instead, it calculates the mutual reachability distance. It mathematically pushes isolated noise points further away, clearing the fog around dense areas. It then builds a hierarchy of all possible density thresholds. But instead of drawing a single horizontal line to cut the tree, HDBSCAN does something brilliant: tree condensation. It tracks the clusters as the density requirement changes. It calculates the stability of every branch using lambda values. How long does a cluster survive as we lower the threshold? If a cluster is just a fleeting artifact, it splits and is discarded. Only the most robust, deeply rooted clusters with high stability survive the test. The result? Perfect clustering, dynamically adjusting to any density, with zero manual epsilon tuning required. That is the true power of modern clustering. We have seen algorithms that are accurate but painfully slow on massive datasets. What if we need lightning speed? Welcome to the speed demon of clustering. FINCH. Instead of calculating a massive, exhausting distance matrix for every single point, FINCH asks one painfully simple question. Who is your absolute closest neighbor? It connects every data point to its first nearest neighbor, or h-NNE. This instantly forms small, localized chains and communities across the dataset. Once these microclusters are formed, FINCH calculates a central point, a centroid, to represent each group. The original points are then condensed into these centroids. Then, it recurses. It treats these new centroids as the base data points, finds their nearest neighbors, and builds a new graph. This agglomerative process scales incredibly fast. But speed comes at a heavy cost. What can go wrong with FINCH? Number 1. Ignoring geometry. At high levels of the hierarchy tree, the number of centroids becomes very small. Look at this dense blob and the winding tail. Visually, they are distinct, but geometrically, the centroid of the tail might actually be closer to the centroid of the blob than to its own extremities. When FINCH forces a h-NNE connection, it brutally breaks the natural cluster. Flaw number 2. The density blind spot. FINCH does not detect density on the data manifold, but relies purely on ambient space. Unlike DBSCAN, FINCH lacks a robust noise filtering mechanism, because the strict rule is that every point must connect to its nearest neighbor. Noise points cannot be ignored. Outliers will latch onto the nearest valid cluster, heavily skewing the results. To solve this, data scientists often pair FINCH with supplementary tools like UMAP or t-SNE to preprocess the space. So, we have an arsenal of algorithms, but in the unsupervised world of big data, a terrifying question arises. How do we know if our clusters are actually any good? We divide evaluation into two philosophies. First is internal criteria. This evaluates the goodness of fit purely based on geometry. It calculates two things: cohesion, how tightly packed points are within their own family, and separation, how far apart different families are. You want maximum tightness and maximum distance. Second is external criteria. This is for when you actually have ground truth labels and you want to test the algorithm like an exam. It measures alignment. If the algorithm groups a set of points together, do those points share the same original label? It penalizes the algorithm for mixing different classes. Now, what about the number of clusters? The brutal truth is, there is no magic number. It is highly subjective. In textbooks, data is clean. In reality, data is overlapping, heavily noisy, and filled with ambiguous boundaries. Trying to force a specific K is often a fool's errand. That's why dynamic algorithms like HDBSCAN are the future. But eventually, in the era of big data, accuracy means nothing if your code never finishes running. Let's talk about the ultimate bottleneck: runtime. If we plot execution time against a massive scale of up to 1 billion data points, a terrifying hierarchy emerges. Hierarchical algorithms like HACK and DBSCAN shoot up exponentially. They simply cannot handle massive scale without exploding in runtime. Probabilistic models like DPGMM and GMM grow linearly, but have a very steep slope due to heavy matrix calculations. Standard partition models like K-means++ and K-means perform much better, acting as the industry workhorses for general tasks. But look at HDBSCAN and especially FINCH at the absolute bottom. FINCH operates strictly at O(n). staying flat and ripping through a billion points effortlessly. In big data, you must balance the mathematical purity of the algorithm against the brutal reality of computational limits. We have mastered the theory. Now, let's step into the real world. How do tech giants use clustering in production? Case Study 1. Multimodal Retrieval. Imagine searching for a brand using both text and video content. A deep learning encoder acts as the translator. It takes these vastly different inputs and projects them into the exact same embedding space. Here, clustering takes over, matching your search query with the nearest visual centroids. Case Study 2. Semantic Data Annotation. When processing millions of text reviews, reading them sequentially is humanly impossible. Clustering groups similar textual meanings into visual families. This allows data engineers to label thousands of data points with a single click, creating an exponential speedup. More importantly, it provides robust outlier detection. That one weird point floating far away from the main clusters. That is an anomaly, a mislabeled error, or a piece of noise. By isolating these errors, we transform a raw, noisy dataset into a curated, highly reliable foundation for AI. To summarize the impact of clustering in modern pipelines. Number 1. Exponential speedup. We process data in massive parallel batches, not sequentially. Number 2. Robust outlier detection. Automatically catching edge cases and structural errors without human intervention. And number 3. High-quality curation. Ensuring the data feeding our machine learning models is as pure and structured as possible. From Gestalt psychology to multidimensional embedding spaces, clustering remains the backbone of unsupervised learning. Thank you.